Okay, so talking about branches, just to recap, um, this is really all to do with the simple fact that when you take angles, then when you measure an angle, you measure it, it starts from 0 and then goes to pi. Then you have an option. You can either say, well, I'm going to choose my angle to go from 0 to pi and then stop there and then jump and go from minus pi back to 0. Or you can say, well, I'm going to take my angle to go from 0 to 2 pi, and then when it gets to 2 pi, I'm going to jump back to 0. The jump causes problems with certain functions. And basically, the key function it causes problems with, which results in problems with other functions, is log z. And we've seen this because we know that log z is defined like this. So it's log of the distance plus I times the angle. So if the angle has a sudden jump, that means log z is going to have a sudden jump. And the branch cut is where the sudden jump occurs. Now, we can choose where to put the branch cut. We can decide that, okay, if we measure angles going from minus pi up to pi, then the branch cut will be along here. If we decide to measure angles from 0 down to 2 pi, then the branch cut goes here. We could also do something different. We could say, well, I'm going to measure angles going from plus 135 degrees to minus whatever that is. So you can choose where to put the branch cut, but the branch cut has to go somewhere. Branch cuts, the examples I've shown here, the branch cuts are semi-infinite in the sense that they have one end, the other end goes off to infinity. In principle, you can have a branch cut which has no ends. But basically, wherever there is an end, we call that a branch point. Now, for log z, the branch point is at z equals 0. Okay, so where do we get to? Now, suppose we have a function f, which contains either log of g or g to the power g to the power alpha. What then are the branch cuts of the function f? So the general technique that I suggest is that the easiest thing to find is actually the branch points. And these are basically wherever g of z is 0. Why? Well, because we know that when the argument of log is 0, then that's where you get a branch point. Okay, so the branch point arises from the fact that we get a branch point of the argument at z equals 0, and log z involves the argument theta. So we first look where g of z is 0, and that will be where we get a branch point, or more than one branch point. And the same with g of z to the power alpha, because g of z to the power alpha, remember, is defined in this way. It's g of z can be written as e to the alpha times log z. So we still have the log z there. So again, with either of these, we just look for when gz equals 0. Then if we have decided that log and raising to the power alpha have branch cuts along some angle theta equals phi, where normally phi is either 0 or pi, then the branch cuts of f of z are wherever the argument of this, the argument of g, is equal to phi, where normally phi is 0 or pi. So an example is when you've got log of z minus z naught, then g is obviously z minus z naught, or you've got z minus z naught to the alpha, then g is obviously z minus z naught. So the branch point is whenever this g is 0. So in that case, it's going to be when z equals z0. And basically, the branch cut just needs to be translated by an amount z0. If you have log of q times z, and maybe z is z minus n0 or something else, and q is a function is in the complex numbers, then the branch cut will be whenever arg z is equal to phi minus rq. This is maybe a bit more complicated example, okay, I mean that's fairly straightforward to see. Basically, this follows from the fact that the argument of a product of complex numbers. So you've got product q times z here. The argument of that is going to be argument of q plus the argument of z. And we want that to equal, it's going to be a branch cut when that is equal to phi. Okay, this is maybe a more abstract example, which is a bit more complicated than we actually need. But anyway, if you have a situation where you've got q times z and you want to find the branch cut of log of qz, then it ends up being rotated by rq. Anyway, let's actually see an example, and things should become a bit more clear. So we want to find the branch cuts of the function root of e to the z plus 1. Okay, so this is quite a complicated function to find branch cuts of. Why we get, well, the first thing to understand is why do we get branch cuts? Well, it's basically because we've got a square root. If you have a square root, that means it's a multi-value function. It can be plus or minus, so it's multi-valued. We expect more than one branch, so there should be a cut somewhere. Right, so if we choose the usual principal branch of the square root function, that means we choose the branch cut along theta equals pi. Basically, that means we're taking the argument of a complex number to lie between minus pi and plus pi instead of between 0 and 2 pi. So, as suggested, we first find the branch points. So the branch points will occur when the thing inside the square root is equal to 0. So this is going to be equal to 0 when e to the z is equal to minus 1. Now, when is e to the z equal to minus 1? Well, basically, you might remember that e to the I pi is equal to minus 1. And we can always add 2n pi I to the thing inside the e and get the same result. So basically, z is equal to 2n plus 1 pi I are the places where we get branch points. So we have infinite number of branch points. Okay, these values. So these values are along the imaginary axis, spaced 2 pi apart. Right, so next we need to know, we want to find out where the branch cut is, or there'll be more than one branch cut. So remember that from every branch point there must be a branch cut. So we've said that we're using the usual principal branch of the square root. This basically means that if we just had the square root, then the branch cut would look like this. So basically we're saying that we're going to have problems whenever the thing inside the square root is negative and real. That's where the discontinuity is going to occur. So you look back at this and we say, where inside the square root, when do we get negative real numbers? For what values of z do we get negative real numbers? That's the question we have to ask. Okay, so it's basically where e to the z plus 1, which we can also write as e to the x times e to the iy plus 1, is real and negative. So this requires a little bit of thought. It's only going to be real. Well, obviously e to the x is always real. It's only going to be real if this is real. So e to the iy, when is that real? Well, that's real when y is n pi, right? Then it would be either going in the, e to the I n pi, where n is even is 1, and when n is odd, it's minus 1. So that's the only possibility for it to be real. Now, e to the x is always positive, and we want negative. So that means this can only possibly be negative if e to the ey is actually minus 1. So that occurs if y is 2n plus 1 pi. So we've got the y values. So knowing that this is now minus 1, we've got 1 minus e to the x. So what values of x do we need to get that to be negative? Well, obviously, when x is 0, then e to the x is 1. When x is more than 0, 1 minus e to the x will be negative. So the branch cuts, therefore, summarizing, are the lines x plus 2n plus 1 pi I, where x is greater or equal to 0. Okay, so we've got the values. It's anywhere when x is greater than 0 and y is equal to n plus 1 pi. Okay. So question 11 is talking about exactly the same function, but read the question carefully. It's now asking you to do, instead, consider what happens when the principal branch of the square root is along theta equals 0. So we have this situation here. The example we did was with this situation. Now we've got this situation here. That means, okay, well, I won't give you any more clues, but the answer is not going to be the same as the example. So it says, find the branch cuts of this and comment on whether the branch cut structure on the complex plane is simpler or more complicated than this example. So you should probably draw the branch cuts in this case and draw the branch cuts in this case and compare. Okay, so now what about other multi-value functions we've met? Well, we've met inverse trig and inverse hyperbolic functions. They can both be written in terms of log and raising to the power alpha. So their branch cuts can be found by considering the branch cuts of log and raising to the power alpha as well. So really, we've already covered those cases.